Hey guys, Mr. Backwork here. In this video we're going to take a look at 12 basic functions and their graphs. Our first function that we're taking a look at is the identity function, and that's just the function f of x equals x. When you graph this one out, you get a nice straight line that goes through the origin and has a slope of 1. Our next function is the squaring function, and that's f of x equals x squared. When you graph this one out, you get a parabola shape, and parabolas have some nice reflective properties which make them useful in satellite dishes, flashlights, car headlights, anything of that sort. Our next function that we've got is the cubing function, so that's f of x equals x cubed. As we're looking at this graph, two things are happening around the origin. As we look at the picture, it looks like our graph kind of flattens out, but it does keep increasing the entire time. The change is just so small that our calculator has trouble showing that on its pixels, so it looks like it flattens out there. One other thing that happens is if we look at the right-hand side of this graph, this part is curving up, and if we look at the left-hand side, this part is curving down. So the origin here is called a point of inflection because it's where our graph changes its curvature. You might hear that referred to as concavity. So the right-hand side, since the curve is going up, we would say that's concave up. But on the left-hand side, since the curve is going down, we would call that concave down. Our next function is the reciprocal function, so we've got f of x equals 1 over x. When we graph this one out, we get a hyperbola shape. Hyperbolas also have some reflective properties a lot like parabolas, so they can get used for satellite dishes and radios and TV. They're also used in microscope lenses, and they can also be used when we're tracking the motion of launching a satellite into space. Our next function is the square root function, so we've got f of x equals the square root of x. We're starting at the origin and we're working our way out to the right-hand side. There's nothing on the left-hand side here because you can't square root negative numbers. Our next function is the exponential function, so we've got f of x equals e to the power of x. So you'll notice that that x variable is up as the power. E is actually an irrational number, a lot like pi. And it shows up in a variety of different applications. Using pi and e to represent those irrational numbers was brought into use way back in the 1700s by the Swiss mathematician Leonhard Euler. Our next function is the natural logarithmic function. So here we've got f of x equals the natural log of x, written as ln of x. As we look at the graph, there's nothing happening on the left-hand side of our graph, because a lot like square roots, we can't evaluate logarithms of negative numbers. Our next function is the sine function, so we've got f of x equals the sine of x. And as we look at the graph, we've got these waves that keep bouncing up and down, oscillating up and down. Anything that has repeated behavior can be modeled with a sine function. So if you're tracking something like the tides of an ocean or the position of the sun in the sky throughout the day, or even temperature, all of those things can be modeled using different types of sine functions. Our next function is the cosine function, so now we've got f of x equals the cosine of x. Our cosine function has a lot of similarities to that sine function. We've got repeating waves bouncing up and down. So it's got a lot of the same properties and can be used in a lot of the same ways as a sine function. Our next function is the absolute value function. So we're looking at f of x equals the absolute value of x. All of our other graphs have had nice smooth curves to them, but as we're looking at this one, there's a pretty abrupt change at 0. It's got a pointed corner versus being a nice smooth turn like we've seen in our other graphs. Our next function that we've got is the greatest integer function, and you might see this one written a couple different ways. You can just see it written as f of x equals int of x, meaning the greatest integer, or you could see f of x equals this x inside of these square brackets with kind of this double vertical bar on either side. As we look at the picture, we've got all of these different horizontal chunks of our graph, so we've got jump discontinuities between each piece. Graphs that look like this are called step functions because they have kind of a stair-step pattern to them. our last function that we've got is the logistic function. So we've got the function f of x equals 1 over 1 plus e to the negative x. This graph actually has two horizontal asymptotes. It's got a horizontal asymptote at y equals 1 and also at y equals 0. Logistic models get used a lot when you're talking about things in biology and also in business. Now, as we're thinking about those functions and as we're looking at our graphs, 9 of those functions had a domain of all real numbers, meaning that you could safely plug in any number for x that you want and you would always get back an answer. But 3 of them do not, and we want to identify which ones don't. One of them that we saw is f of x equals the square root of x. We have to be very careful about those x values that we're plugging in, making sure that we're not including any negative numbers. Another function we saw was f of x equals the natural log of x. A lot like square roots, I said that we can't evaluate logarithms of negative numbers, so this would exclude the negative numbers from its domain. And our last function is going to be that reciprocal function 1 over x. Almost everything is safe to plug in there, but 0 would be a bad number to plug in because you can't have 0 on the bottom of a fraction. We can also look at our graphs to figure out continuity for our functions. Remember, a graph is continuous if we can draw out its entire picture without needing to pick up our pencil. So almost all of those graphs are continuous, but there's a couple that aren't. One of them that is not is that reciprocal function, f of x equals 1 over x. Because we have to exclude 0 from the domain of that function, there's a vertical asymptote at 0, so we would have to pick up our pencil to jump over that vertical asymptote to continue drawing the rest of the graph. The other one that's not continuous is that greatest integer function, so int of x. And that one was our step graph, so it had all of those different jump discontinuities between each horizontal chunk of the graph. And one other thing that we can see as we're looking at the graphs of all these different functions is boundedness. And we're going to have 3 functions that were bounded. And remember, bounded means bounded both above and below. So our sine and cosine functions are each bounded. If you look at the graphs for those, we had those oscillating waves bouncing back and forth between 1 and negative 1. Our graph will never go above 1 and it will never go below negative 1. So we're bounded above and below. Our other one was that logistic graph. We said this one was going to have horizontal asymptotes at 1 and at 0. So because there's horizontal asymptotes, our graph is going to be bounded between 1 and 0. We can also take a look at our graphs to figure out symmetry. 3 of those 12 graphs that we looked at were even, meaning that they had y-axis symmetry. And remember, y-axis symmetry means the right side of our graph looks the same as the left side of our graph. One of those even functions is f of x equals x squared. Because if we think about that parabola, the right side and the left side have the exact same behavior. If we were to take the right side and fold it over the y-axis, all of those points would match up with the points from the left-hand side. We've also got our cosine function, f of x equals the cosine of x. That one is also even because it has y-axis symmetry. And our last one, f of x equals the absolute value of x. That one also has y-axis symmetry, so it's even. That's going to be it for this video. Thanks for watching.